So now we're talking about blockchain structure. So last time we talked about basically like high-level principles of what we're trying to do and like the high-level abstraction of agreeing on a shared history, specifically of a state machine. And then we talked about like the technical model of a state machine. So this time we're going to start to talk about the actual blockchain data structure. So if you remember, I said like you could think about 3 parts of the blockchain: the state machine, the data structure, and the consensus. So this is the data structure part. So let me get my speaker notes here. Okay, bring that over here. All right, so here we go. So here it is. This is our first picture of a blockchain, I think, right? We finally made it, guys. We got a blockchain. Hooray. Let's see what goes inside of it. Blockchain cryptographically guarantees that a history of events hasn't been tampered with. So it allows all the interesting parties, so basically you can think of like the users and service providers, to have a shared history. So what we're going to do now is see how we can use cryptography to enforce that like common shared history that I talked about before. So here's the core idea of the blockchain data structure. It's a hash-linked list. So each one of the blocks has a payload in it. The payload is like totally abstracted. Different blockchains have different payloads. Here I'm showing like a human readable story. So you can see we have this like common story here. It says, then Alice jumped out the window and broke her legs. But a different story might start out the same. Then Alice jumped out the window and found that she could fly like Icarus. So the idea here is that like our story can diverge, you know, and we might even have a common prefix of what happened for a while, and then have different paths of the story. So later in consensus, we're going to talk about how we agree on which one's the real one. But for now, we're just going to look at how these different payloads are cryptographically linked, so that anyone can know that this story is different than this one. Because a lot of times what you'll see is that like a story might diverge a little bit, but then they'll have a whole bunch of the same sentences. But that's still important because like imagine you have a story about some conflict, and a lot of times which side you want to side with really depends on how this whole thing started, which may be way back deep in the history. And so what we want is a really fast way, or basically an O of 1 way, to know whether 2 stories are truly identical throughout their entire history or if they're not. We don't want to have to iterate through every block in the story. So here's how we do it. Each one of these blocks can be hashed. I know you guys learned about hashing algorithms. I'm representing that with this stack of hash brown potatoes here, one of my favorite foods. So if you just imagine taking this block, throwing it through your favorite hash function, whatever it is, any cryptographic hash function will do, and you get some hash out of it. So here's the key step. This is probably the most important point in the whole lecture. What we do then is that we include in each block the hash of the parent block. So you can see here in the second block, we still have the payload. That's like the actual data. This is the shared story that we're trying to reach agreement on. That's like the whole reason for doing this. And then here's the implementation detail that makes it all work cryptographically, and that's the parent hash. So you take the hash of the previous block, you throw it into this block. So whenever you want to add the next bit to this story, then maybe she like flies too close to the sun, you make your block, you fill in the payload about flying too close to the sun, and then you take this hash, 576D, and you put it as the parent hash in your next block. So this cryptographically links every block in the whole chain, and that gives us an O of 1 way, or a constant time way, to check whether the entire history of 2 stories is equal or not. Because if you just look at any 2 blocks, if they don't have the same hash, that means they're not the same story. So even if I added another block right here that had this same exact line, could fly like Icarus, the hash would still be different because some of the data that goes in there would be different. It doesn't have the same parent hash. So this is what's called like cascading hash effects. Because you continue to build on the parent, if you change it at any point, every subsequent hash changes. So it's actually like very similar to a Merkle tree, how if you change like any one leaf in the Merkle tree, then everything above it all the way up to the root changes. Okay, great. So that's like the core idea. Go ahead. This idea of a hash-linked list, I feel like it must. I can't think of a specific example. For sure, like cascading hash data structures predate Bitcoin. Yeah, I'm 100% sure about that. Yeah. Okay, so here's the slide that I thought about earlier. This is like, in the same way that we talked about Genesis state when we were talking about state machines, now we're going to talk about the Genesis block in a blockchain. So every blockchain starts somewhere. That's called the Genesis block. And since it doesn't have a parent, it's hard to know what to put for parent hash. So basically what happens is that everybody agrees, just as part of the protocol, like the parent hash is some very specific hard-coded value. And it really truly doesn't matter what it is, but it's most common to just choose like the all zero hash, and that's what I've shown here. And the reason that you choose that is just because like any human can look at it and be like, oh, that's the zero hash, this must be the Genesis block. But the point is, like, you just agree on some arbitrary parent hash, and then you start building the blockchain from there. Here's how we're going to marry up our blockchain, which so far I've just shown containing like human-readable English payloads with our state machines. So the key idea is that what you include as the payload is no longer just a sentence, it's actually a state machine transition. So what I've shown here is that every block contains one transition. We'll see that like in reality it's a little bit more complex than that, and I'll get to that very shortly, but this right here is the core idea. The payload is a state transition, and the parent hash is what cryptographically links the entire history together. So this is sort of like the simplest way that you could build a functional blockchain. And everything beyond this is optimizations. Now there's like super important optimizations, don't get me wrong. Like you don't want to go build your production blockchain in this like kind of dead simple way, but for sure this is the core idea right here. We have the cryptographic linking and we have the payloads, which are state machine transitions. So where do the states live? Well, not in the blocks, okay? This is a key idea. The states are not in the blocks. They live somewhere else. Okay, question, where do the states live? Not in the blocks. Don't make that mistake. It's a common mistake. The states don't live in the blocks. The states can get very big if you think about like storing every Ethereum smart contract code and every token balance and like blah, 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 whatever arbitrary data your blockchain is going to store. It's too big to put in the blocks. So the states don't live in the blocks. The states don't live in the blocks. You have to store them somewhere else. So in practice, that's going to be like some external database. But the idea is that the idea is the same as before. If you agree on the Genesis state and you use this cryptographically linked tool, data structure, the blockchain, to agree on the state transitions, then you'll be able to recompute any state. And then depending on how much you care about having all the states available, you might like want to allocate a bunch of disk space to tracking them all, and that's totally fine. You're welcome to do that. Many people do. Or you might want to only track like every 100th state. And then if you want to reproduce one that's in between, you just like go back to that one, most recent one that you have stored and re-execute a couple state transitions on top of that. Or what some people do is they like store all the recent states and throw away all of the old ones, because most of the time what you're interacting with is like the latest state. But the key idea here is that they don't go straight inside the blocks. Now, in some ways, it would be nice to have the state information in the blocks. The reason we don't is because it's way too huge. That would be like major data bloat. And like most of the state typically doesn't change from block to block, so it would be super redundant. The one nice thing that we do want to get is the ability to like link a state to a block, so that if you like, let's imagine you keep track of the entire history of the blockchain. A lot more people keep track of that than also all the states. So what you want is the ability to say like, okay, I have this whole blockchain. I'm curious about state 6,000. I've like recomputed this thing that I think is state 6,000. I'd like to just like be able to know that this is indeed the same state that everybody else was using. And the way that we achieve that is through a state root. So I'm expanding my block here. We still have the cryptographic linking between blocks. We still have the payload, which is a state transition. And now we have a state root. And in practice, this is typically a Merkle tree root. So you somehow like build your state into a Merkle tree. Every blockchain does it different. And you attach the root there. But like at just a slightly higher level of abstraction, you can think of this as like any kind of cryptographic fingerprint. So what you could do that's like a little less performant would be to like just take the entire state and hash it and put that hash in here as the state root. The Merkle tree idea is a little bit better in practice, but the idea is that whenever you see some state and you say, okay, I think this is the state that goes with block like 10,000 or whatever, you can just check. You just recalculate from your state. You calculate that fingerprint either by hashing it or building the Merkle tree and getting the Merkle root, and then you see if it matches here. So again, what we see is like a cryptographic linking between the block and the corresponding state. So we now have two linkings. One is back to the parent block, and one is to the associated state. Okay, comments or questions so far? Okay.
So if the state doesn't live in the block,
That's right.
how can you ensure that someone will carry the state? Right?
Yeah, I mean, you can't, and a lot of people don't carry the state, and that's normal. You know, like at least what people often do is keep the state near the tip of the chain, near like the current part of the history. So in the same way that one might be like relatively informed about the state of the world today, you know, like knowing where their friends and families are, knowing what countries they are, knowing like when they're planning to fly back after the academy, they wouldn't know that same level of detail about what happened like 100 years ago or 1,000 years ago. And kind of the same thing happens in blockchain. Do you want to say something? Oh, okay. All right, cool. Yeah.
Is there any difference between like the on-chain and off-chain aspects of it? So I'm guessing like the state is not stored on-chain, it's given it's not inside the block. So where does that live?
Yeah, so whether it's stored on-chain, so it's definitely not stored in the blockchain data structure. It is cryptographically like attested to in the blockchain data structure. But typically when someone says something like, are the balances stored on-chain, or is this or that data stored on-chain? What they really mean is that data stored as part of the state? Okay, so the word like on-chain there is a little bit fuzzy. You know, I would say like in Ethereum, the smart contract code is stored on-chain. That doesn't mean it's literally in the blockchain data structure. It means it's in the state, which is attested to by the state root, which is in the blockchain data structure. Great question.
I have a question. So if I, for example, if something bad will happen and I will lose the state, so
Yeah.
I understood that I can recreate the state from the transaction history, yeah?
Yeah, exactly. Yep, that's right. Yeah, so let's say you're like really interested in keeping all the states and then you have some like catastrophic disk failure. It's not the case that you're like hosed forever. You just go back to the Genesis state and you replay the blockchain block by block by block, and you iterate, and you know like, okay, if we started at this state with the light switch off, and then we had this transition where we toggle the switch, then it must be on. And if we're now on and then we toggle the switch, it must be off, for example.
Okay, so what is the point to keep the states?
What'd you say?
What is the point to keep the states? Because it takes data, yeah? So if I can recreate, it is enough to have the last one, yeah?
Yeah, that's right. So that's one of the points I'm making. It's like not that important to keep all the old states. One thing that we'll see is that it's important to keep at least some recent states, because sometimes the blockchain forks. That's coming up soon. We'll talk about that like in the next few minutes. And like some people do sometimes want to like be blockchain historians and look back. Like you might want to know, okay, how many tokens did I have at this time last year or something like that? And for that, you need to know the state from this time last year. So a lot of times what people will do is they won't store all the states themselves. Instead, they'll like call up some block explorer and be like, hey, block explorer, what was my balance at this time last year? And then the block explorer tells them. Now, they do depend on the fact that someone's out there who's willing to tell them. If no one's willing to tell them, the only option is to recompute from Genesis. But if there's anyone out there who's willing to say, like, here was your state at this time last year, you don't have to trust it. You can check against the state root and see if they told you the real thing. And if they lied to you, you'll know. Yeah.
Okay. There is no Merkle tree inside the blocks? I mean,
so the Merkle tree is not inside the blocks. Take your state here, and imagine you split it up somehow into a bunch of leaf data. You build the Merkle tree. Only the Merkle root goes inside the blocks. And that's why I'm saying, like, I don't want you to get too obsessed with knowing there's a Merkle tree here. It's almost always true that there is. But just think of this as any kind of cryptographic witness. An alternative way would be to just take this struct, whatever it is, throw it through a hash function, and put the hash right here. And that would be less performant, but would still have the same cryptographic guarantees. Great, we're here already, forks. So we already know that a state machine can have different possible histories, and they're called forks. So you can think of them as like alternative realities, and we need to decide which of the many possible forks is ultimately like the real one, or the canonical one, as it's often called. And this is like the main job of consensus, which we're going to talk about in 2 upcoming lessons in this module. The first one's this afternoon, and the next one is tomorrow. But for now, what I'm trying to point out is that although we call it a blockchain, it isn't the case that it's strictly linear. Kind of like a better term would be to call it a block tree, where the genesis block is the tree root, and then there's forks all along the way here. And it's the job of consensus to decide, like, this isn't the real one, this isn't the real one, this is the real one. And then once you've decided which one's real, then you can trace like a canonical chain all the way back to Genesis. So forks exist, and this is the reason why it's important to keep a few recent states. Because maybe at first you've only seen like these blocks near the bottom, and so you think like this is the real state, but then later you hear across the network someone says like, hey, actually there's this other block that you should know about, and it turns out it's like this one or this one. In order to execute these blocks and know what the state is, like you still need to know the state from back here. So that's why it's usually good to keep like at least some recent states, because blockchains, so this isn't true for every single blockchain, but as a generalization is true that blockchains don't give you instant finality. They usually do give you strong finality guarantees, but they're not instant. And so, you know, sometimes you'll have this thing called a reorg, which is coming up shortly. Okay, right, so invalid transitions. So imagine someone tells you about a block that says, the light switch was on, and then I flipped the switch, and now the light switch is on. That's not right, right? If it was on and I flipped the switch, it has to go off. So some of these blocks are going to contain invalid transitions, and we throw them out right away. Before we even get to the heavy-duty consensus stuff, each node in the network will validate the block and make sure that it's at least a valid story according to the state machine rules. And then what we're left with, in this case, like 1, 2, 3 candidates, then we'll use consensus to decide among those. I'll repeat that again later in the consensus lesson.
So in a block time of, say, 6 seconds
Yeah.
or 12 seconds,
Yeah.
what are we saying is happening in that block time?
Yeah, okay, right. So this question is mostly for the authoring lesson, so I'll answer it very briefly now, and if you want to dive deeper, ask me again this afternoon, but let me just go like real quick. Let's say that this block was created at time t, t0, we'll say, whatever it is. That means that if people are following the protocol, the next blocks, so there's 2 of them, it's not always the case that it's the next block, in this case it's the next blocks, should each be created about t0 plus 6 seconds. And then the next children there, so like these ones, the next generation of blocks, you can say, should be created at t0 plus 12 seconds, and then t0 plus 18 seconds.
Okay.
And so when you look back at your canonical chain, like let's say we go through the whole consensus protocol, we decide this is like the real best block, and so this is the real chain here. When you look at that chain, you'll see a chain of blocks where each one came like roughly 6 seconds apart.
But in that 6 seconds, we don't know which block is the right one yet. Right?
Yep, that's right. That's exactly right. So there are some consensus mechanisms where like the moment a block is official, it's also finalized. They have, I mean, it sounds like a strength, right? And it does have some strength. There's also some significant drawbacks, which we'll talk about later. But for the most part, yeah, like you don't know, especially near the tip, which blockchain is real. We call it like chain candidates basically. Great question. Okay, one more, then I'm going to keep rolling. Juan. Okay, so I mentioned that like as we were going through this, I was showing you like the core ideas, starting with the most important part, adding the like progressively less important but still important parts. So let's get really serious now. Here's the most realistic blockchain structure that I can show you yet. So the block is actually split into a header and a body. The header is basically like a minimal summary of the important information about the block. And then the body is essentially the state transition, but it's, as you can see here, it's actually not one transition. It's like a batched ordered list of state transitions. So Michael already hinted that like in most real blockchains, there's some block time, either deterministic or probabilistic. And so like we wouldn't want to only have a single state transition every 6 seconds. Or like in Bitcoin, imagine if you could only have a single payment every 10 minutes. That would be like such low. I mean, Bitcoin's already low throughput, but it's not that low throughput. So really what happens in a block is that in the body, you're batching. This is like a vector of state transitions. And then the header is actually what's hash linked. So remember I said there's always a parent hash. Well, it's actually the parent header hash. So this header contains the hash of the previous header, which contains the hash of the previous header. And so this is how the block is divided. It's divided into the header, which is like the minimal cryptographic information, all of the cryptographic linking, both to the state and to the previous header, and a few other things that I'm going to show you shortly. And then there's the body, and this is the bigger part, the like more data-heavy part, where all the state transitions live. And so in the same way that I said some people choose not to keep all of the states, it's also the case that some people choose to not even keep the bodies and only keep the headers. So let's see, where do we go next? Yeah, so a little bit of code. This is what blocks look like in Substrate. So just a quick reminder, this is not the Substrate module. This is just to show you like a typical way to build a block. It's basically a struct. It's generic over a couple of things. The most important one is like extrinsic. So this is another synonym for transaction or state transition. So there's lots of words that mean the same thing. And then the header type. And so a block basically is a header, and then the body, and the body is a vector of extrinsics. This is basically the code way of showing the exact same thing that I'm showing pictorially in this slide. So these are like two depictions of the same concept. Okay, so let's look at headers here. The exact content that goes in the header varies on a blockchain by blockchain basis. It always contains the parent hash. That's like one of the first things I showed you and one of the most important things. That's how we have a cryptographically tamper-proof shared history. So that's always going to be there, and it always goes in the header. It's the headers that are cryptographically linked. Yeah, okay, that's it. So let's look at a few. So we're just going to look at Bitcoin and Ethereum, two of the most famous blockchains. So they have some commonalities here. Previous hash and parent hash. They're called like different names, but they mean the same thing. They have the Merkle root for the transactions, and this one has like the state root. They have some consensus-related things. Oh, this is actually Ethereum pre-merge because it still has like a proof of work difficulty. And then many blockchains, including substrate-based blockchains, include actually the block number or the block height in the block header. And so what I mean by like block height is basically like if you start at the genesis block and call it 0, and then you go block by block by block and count them up, 1, 2, 3, 4, that's the block number. And it's not strictly necessary to store it in the header. Bitcoin doesn't, but it's like pretty nice to store that in the header, and most modern chains do. Okay. So let's look at substrate headers. So again, it's not the substrate module. We're not going to go super deep here. But I think that this one's really useful because substrate is meant to be a generic blockchain framework. And so by looking at what's in a substrate header, it gives us a sense of like what are the most important things that we typically need to see in a blockchain header in order to build like almost any kind of blockchain. So here's the most important one for sure. This is the cryptographic linking over the shared story. The number's not as important, but it's pretty nice, and it's in there in Substrate. Here's the state root. We already talked about that. That's the cryptographic linking to the state. By the way, where do the states live? Awesome. And here's one that I haven't mentioned yet. This is the extrinsics root. So once we moved the extrinsics into the body of the block, and I told you that some people don't store that, some people only store the headers, we need a way to cryptographically link the extrinsics back to the header. So in the same way that the state root is like a Merkle root that encapsulates and fingerprints the entire state, the extrinsics root is a Merkle root that like fingerprints the entirety of all of the state transitions that were in the body. And that way, if you choose to not use up your disk space storing all of the block bodies, when you later hear about one from an untrusted source, you can check to see if it's the real one. And if it's not the real one, they're not going to be able to trick you because the extrinsics root won't match. And then finally, there's this abstract concept of consensus digest. So we're really going to dive into this in the 2 upcoming lessons on consensus. But just to give you an intuition, like if this were a proof of work chain, that would be the mining output. Or if this were a proof of authority chain, that would be a signature by one of the authorities. And that's all I'll say about it for now. Here goes. Mike.
So the extrinsics root root is the Merkle of the extrinsics that exist in the body,
Yep.
but they're not combined with the previous block, like the header.
Yeah, that's exactly right. The only thing that links a header to the previous header is this one, the parent hash.
Okay.
These other two roots, these are all about this block, nothing to do with the previous
Everything
block.
that comes from the body, and that's just verified that
Yeah.
if we don't save the body, then we can come to that state root from the Merkle tree that comes from the body.
That's
just
right.
For checks. Thank
Now,
you.
if you think about like this, imagine we have all this data. Maybe like I have some parent hash. This is block number 1,000, some state root, blah, blah, blah. Like all of these are filled. And then I go to make the next block. I'm going to hash this whole thing, including the state root and the extrinsics root. So all of this causes cascading hash effects into the next block. It all becomes part of the parent hash in the next block. Yep. Great. Okay, so actually I have a slide that shows this a little bit. In fact, here it is. Okay, so here's our header chain. And I've filled it in with the substrate header field. So again, it might look a little bit different in each blockchain, but this is like a nice generic, like typical way to do a header. So this is the core data structure. This is the thing that's hash linked all the way from Genesis, all the way through our shared history, all the way up to now, okay? And again, this whole thing might be forked, but for now, I'm not showing the forks, okay? So here's the sort of like the core, the backbone of the chain. I like to think of the header chain as the like backbone of the whole blockchain data structure. And it has, within the header, it has 3 cryptographic links. One is the parent header hash. That's represented with this arrow. It like points back to the previous header. The number is not a cryptographic anything. It's mostly for convenience. The next is the state root. So that links us cryptographically to the states, which are up top, not in the blocks. And then the third one is the extrinsics root, which links us to these extrinsics, aka transactions, aka state transitions. And I haven't put anything for consensus digest yet because we haven't talked about that yet, but there is going to be some data there. So there's basically like 3 cryptographic pointers, and what they point to is the previous header, the state, and the body. Michael, wait for the mic.
I'm just trying to wrap my head around this. Like, so everyone running a node, these nodes are processing all these transitions.
That's right.
And our extrinsic roots need to be the same
That's right.
while all these transactions are happening simultaneously.
That's not quite right. So what the blockchain is doing is actually establishing an order over the events in history. So if you think back to like the abstract level, I said the main thing we're trying to do here is agree on a shared history. So like, yeah, now we have the question about whether these should be like row major order or column major order. In reality, this is a 1D vec, so all these things are ordered. So like, let's say I'm some blockchain node, I've already executed this block and I know the corresponding state. And then I'm just sitting here chilling, listening for new information to come over the network. And then your node ships me this data packet, which is a new block. So just as a reminder, the header and the body together constitute the block. So what that means is that you've like created a header and a body, serialized it, and shipped it out over the internet, and I'm now hearing about it. So what I do then is I read this state 4, which I already have, and then I go through these state transitions in order. Each step of the way, I'm calculating a new state, new state, new state. And when I reach the end of this list, once, like in this case, I get through all 4 of these things, what I'm left with is a new state, state 5, which I calculated all by myself. And what I do then is I take state 5 and I like hash it or build it into a Merkle tree or whatever, and I get the state root and I compare it and I see, does the state root that I calculated all by myself match the state root that you sent me over the wire? And if it does, then I conclude like, okay, this block that he sent me is valid.
Okay, so another node sends me some transaction.
Yep.
So say I'm a node. Another
Yeah.
node sends me some transaction.
Yeah.
And it's part of the current block.
So when you first hear about transaction, there's 2 ways you can hear about transactions. One is straight from users, like here I am using my like MetaMask or whatever, like trying to send tokens, and I send this transaction out. When you hear about that, that is not yet in a block. And it's like your job as a node to keep track of those and eventually put them into blocks. So that's something that I'm not going into in detail yet. That's called like the transaction pool, basically. It's coming up shortly. The other way that you can hear about a transaction is the way I just described, where somebody sends you a block and that block already contains the transaction.
And that somebody is another node.
Yes, exactly right. That's right.
Now, am I then, as a node, am I then saying, okay, well, I have other transactions and it fits here? Like this actually happened before some of my other transactions. Let me reorder, or no?
So I think there's two different questions that I'm not sure which one you're asking, so I'm actually just going to answer them both.
Okay.
So it's sometimes the case that you hear about a transaction like directly from a user before it even makes it into a block,
Right.
and then some other node sends you a block, and it contains the exact same transaction. And so what you do then is you say like, okay, well, this transaction's in our history now, so I'm going to throw away like this one that I was holding on to, like hoping to put into a block eventually, because like some other node already put it in a block. It's good to go. I don't need to like keep track of it separately. So that's the one question I thought maybe you were asking. But the other one is about forks, right? So like this is a super detailed picture with like all these fields and these crypto pointers. But let me like go back to a simpler one, like this one. So it's often the case that you'll see a fork in the blockchain. This can happen either because a node's malicious, but honestly, it can also happen just because of network latency. And it can also happen because some consensus engines explicitly allow it because it's like good. It has some nice security properties in some cases. And so when that happens, like it may be the case that these two blocks contain entirely different transactions, or they might contain like partially overlapping set of transactions, but in different orders, or they might even contain the exact same transactions, but like just ordered differently. And so when that happens, like we don't yet know which one's real, and we need to rely on consensus to decide that, and we're not talking about consensus yet.
Okay, but as a node, I'm just ordering them within myself.
Yeah, so part of building a block is taking a bunch of transactions you've heard up and ordering them, and then shipping that ordering, basically shipping a block out to the network for everyone else to agree on. All right, great questions. Okay. Wait
We're
for the
going to
mic.
talk about that.
Yeah. Yeah, go ahead if you want. Oh yeah, did you want to say anything, Andrew?
No, I was just saying
okay.
we're going to talk about block authoring in the next one,
Exactly.
which will cover that.
Can I, as a user, have multiple transactions inside one block, like the double spending problem? But is it allowed if?
So
it's
you
fair?
can have multiple transactions. Imagine that I like send some tokens like, to Alice, and then I like buy an NFT from Bob. Those things are perfectly allowed. You can't have conflicting transactions though. You can't like send the same tokens to two different people.
Okay.
That would make the block invalid.
So both transactions can be inside one block.
As long as they're compatible transactions. Like if you think about all these different applications, I can like register to vote in one transaction and then like, I don't know, breed my CryptoKitty in another transaction. So those two things are perfectly compatible. For sure they can go in the same block. Okay. It's only when you do something that like is always disallowed. It's never allowed to send the same tokens to two different people, whether they're in the same block or different blocks. So those could not go in the same block.
Okay, cool.
Yeah. Did you want to say something, Sean? Okay.
Going for the same question, what happens to the transactions if they conflict? Do you throw away both, or do you put one?
You can only ever throw away or keep an entire block. So if any one of these is invalid, we throw away the entire block. And similarly, like maybe there's two transactions in here, and either one of them would be valid on their own, but they're mutually exclusive. You can't have both. Throw away the whole block. Okay, nodes. So we talked about nodes a good amount, but I'll just make sure I don't miss any points here. A node is a software agent, so it's a piece of software that you run on your computer, and it participates in the blockchain network. And there's a whole bunch of different jobs that it might perform. So we talked about gossiping blocks. So like one node will author a block and send it out to the network. it's not a mesh network, which means that it's not the case that every single node is connected to every other single node. It's the case that each node has some finite set of peers. And so if I author a block, maybe I send it out to like everybody in the front row. But then you front row folks are peered with other people in other rows, and you gossip that block out to other people. And so in this way, it's a gossip network. This is basically a P2P network, which Andrew's going to talk about a lot more later on. Okay, so another thing is execute and validate blocks. That's like what I was talking about, where you're like going through the state transitions, applying each one to the state machine to get a new state, new state, new state after each one. And then, okay, right. So many nodes will store blocks. Pretty much every node at least stores the headers. Many nodes store the entire blocks. Some nodes store the entire states, but not many, because that takes a lot of disk space. Another thing is gossip transactions. So that came up a little bit when we had some of those questions. As a user, it's very common for you to send a transaction to one node and rely on that node to gossip the transaction around the network so that all or at least many of the nodes have heard about it. And that way, when whichever node is able to author the next block, they've very likely heard about your transaction. Now, it may be the case that if you only send your transaction to one node, that node might be trying to censor you. So if you're not getting your transaction in, you might consider sending it to multiple different nodes, hoping that you're going to get one non-censoring node who's actually going to reliably gossip it. And if that seems to not be happening, the best thing you can do is always run your own node. That's the way to make the network as decentralized as possible, to run your own node. So yeah, okay, so maintain a transaction pool. So that's kind of what I'm getting at with gossiping transactions. So the transaction pool is a data structure. Like, to think about like a very minimal one, you can basically think of like a hash set or some other kind of set. And it's just a set of transactions that have been sent by users that are not yet in blocks. So a block comes out like every 6 seconds or every however long. It varies from chain to chain. But transactions are coming in from users any old time. Like, I'm not sitting here like waiting for my 6-second timer to go off before I click send in my MetaMask. You know, like, people send transactions any moment, and then they get gossiped around the network. And so the full nodes are maintaining those transactions in a pool. And so then what authoring nodes do, nodes who author blocks, when it's their turn to author, they go to their transaction pool, and they take those transactions and they package them up into a block, and they build a block in the way that we described previously. So like, if your network is like not super congested, basically they just take all the transactions out of the pool, jam them into a block, and ship it off. Now, when the network starts to be heavily used, it's often the case that like there's more transactions in the pool than will fit in the available block space. And when that happens, now the node has a decision to make, and there's no one canonical way to make it. Basically, they have to decide which of these transactions am I going to jam into this block, and which ones am I going to just hang on to in my pool in hopes that they go in some future block. And like, just to give you like an intuition, a simple way you might do it is just take whichever transactions you saw first. A more realistic way that you might do it is look at those transactions and say, which of these transactions are going to pay me, the block author, the most fees, and take those transactions first. Okay, another thing that a node might do is store block headers. Basically, every node does that. That probably should have come first on my list. And then the last one that a node might do is like answer user requests for data. So every time you like look at your blockchain wallet and you want to know like what's my balance, or like how long until I can breed this crypto kitty again, that's all data that's stored in the block state. And so your wallet is basically making an RPC call into some node saying, hey node, I'm interested in this particular piece of state. Can you please tell me what it is? I saw a question, I think, or was that a stretch? A stretch? Okay, all right, you fooled me. We got a question over here.
So my question is, my name is Ayo. My
Thanks.
question is, RPCs, are they P2P servers? Because you said nodes.
Yeah, right. So RPC, it stands for remote procedure calls, and they're not implemented as like a gossip network. So it wouldn't be the case that I would like ask your node for some data and then you would like gossip that request on. It's more like I would ask your node for data and you would like either give it to me or like tell me to F off and not give it to me. But there's no like gossiping it around. If a node either doesn't answer or like gives me some untrue data, then the best I can do is just like ask some other node. And if it, a lot of nodes are willing to answer some RPC requests for data, but the fact of the matter is it costs them resources to do that. It costs bandwidth, it costs like looking up data from the database. So a lot of people will keep their nodes private. So again, like worst case scenario, you run your own node and then you make RPC requests to your own node because you can control whether it answers or not.
It's a good segue to my question. What is the incentive for the node to answer our RPC call? Or to forward the transactions to
yeah. So there's no like strong standard in protocol incentivization for nodes to answer your RPC requests. Some examples of why a node would do that is because it's your own node and you're just telling it to do that. Another one is that you might be paying for some subscription service, like maybe some Infura-like entity or some entity like runs this service where they run a bunch of nodes and subscribers pay them, and because they are paid, like they're willing to answer these things. Another reason is because maybe you've like deployed some application on this blockchain and you want people to use your application, and it's not yet popular enough that people are like willing to pay subscription services for an RPC node. So you're just kind of like altruistically running this node, answering RPC requests about your app, just so that people can use it to try to like bootstrap critical mass onto your app. But none of that's in protocol, to answer your question. Like you need to figure out an incentive for someone to tell you, like to answer your RPC requests.
Hey, I'm Luca. So I have a question. Let's say we have two nodes, right? So I receive a bunch of transactions, but it's not my time to produce a block, right?
Right.
So someone else produces a block, and that affected the same state that my transactions were going to modify. Right. So now all my transactions are invalid?
So, okay, that's a great question. Let me go back to a figure here. Like, what's a good figure? Which one do I want? I guess I want this one. So the idea is like you're listening to transactions. You've got them sitting like over here in the pool. I'm just going to like point to this area of the screen. I know there's nothing there. I'm just like pretending this is the pool, right? It's where transactions go before they go here. It's like the purgatory for transactions, okay? And so it's not your turn yet, right? You're just like waiting on these things. And then some other block comes in. Like let's maybe say you knew about block 4 here, and then block 5 comes in. And all of these transactions get executed, and so the state is no longer what it used to be, right? It's some new state. And so your question is like, what do we do with these transactions? Do we just throw them away? So the answer is like, usually no, you don't, because there's typically a lot of state out there, and the parts of the state that are affected are no longer, or are not like relevant to the transactions that are sitting here. But sometimes it is. Maybe this transaction tries to send like 10 coins to Bob, and this transaction tries to send the same 10 coins to Alice. So in that case, you do have to throw this one away because it's no longer valid against the new state. So the implementation varies. You could revalidate the entire pool every time you get a new block. In practice, for like reasonably busy production chains, that's like a little computationally expensive. So what you actually do is just like revalidate the transaction pool like at some fixed interval, like I don't know, every minute or something like that. And the worst case scenario is like, let's say that you do have a transaction in your pool and it does conflict with this transaction that just came in a block, and you haven't revalidated yet. And now it's your turn to go and author a block. You just grab these transactions out of your pool, and as you're building your block, you're checking them then. So if you like, when you get to this one that conflicts, you go and you apply that, and you're like, oh crap, this is an invalid transaction now. Maybe it wasn't invalid originally. It would have been fine on state 4, but it's no longer fine on state 5. So you're not going to put that in your block, because if you do, all the other nodes are going to throw it away. You're wasting your time. So you just like throw that transaction away like in real time at that moment, and you just don't include it. But so that's like the less likely scenario. I just want to reiterate, the most likely scenario is that the transactions are pretty orthogonal. They're usually still going to be good on the new state. So types of nodes. Okay, so I've already indicated that there's this whole list of tasks that a node may choose to do, and different nodes will choose to do or not do different tasks. And so there's some like semi-standardized labels for these nodes based on what they do. Now I want to be clear, like these are not 100% well-defined. You might have a node that's like basically a full node, but actually doesn't do this one thing that full nodes usually do. Or like a node that's basically a light node, but actually does this like one other thing that they don't normally do. That's totally fine, and most blockchain nodes have like CLI flags or configuration options so that you can specify like, am I going to maintain a pool, yes or no? Am I going to store the states? If so, which ones and how many? But this is just like a general framework for like knowing what nodes typically do. So full nodes, this is like, I would say like kind of the most common or default kind of node. And what it does is it runs a transaction pool. It gossips transactions, it gossips blocks. When it hears about blocks, it executes them, it stores some recent states, and it follows consensus. The next one is light nodes, aka light clients. And light clients do a lot less. They don't download whole blocks, they only download headers. And since they don't even download the whole blocks, obviously they don't execute all those transactions, they only keep track of the header chain. And any time that they want to know something about a transaction or about a state, they have to ask some other node for that information, and then they validate it against like the state root or the extrinsics root or whatever. Okay, so then there's authoring nodes. Authoring nodes are basically full nodes that have the additional duty of authoring blocks. So like in Bitcoin and other proof of work chains, these are called miners, or like in most proof of stake or proof of authority chains, they're called validators. That's what authoring nodes are. So then there's archive nodes. These are the big beefy ones. These guys hold on to the whole block history of the whole chain, or at least a big part of it. They hold on to all the states. A lot of times they'll even index that data into some kind of like more traditional database, like a MySQL database or whatever your favorite database is. And an archive node is like the underlying infrastructure that block explorers are built on. These guys have big disks and they hold on to all of the data. And then there's RPC nodes. And RPC nodes, it's really honestly like not orthogonal to these other ones. Like an RPC node is typically also a full node. It's typically not an authoring node, although it could be. It's not impossible. And basically what distinguishes an RPC node is that it's willing to answer people's RPC requests for whatever reason, and we listed some of the reasons. So when you think about like running a blockchain node, like if there's no additional information, it probably means a full node, but it could be any one of these things. These all count as blockchain nodes. Okay, so I actually think I talked about the transaction pool enough. Let me just make sure I didn't miss any points. Yeah, so this thing is sometimes known as the mempool. Mempool and transaction pool are synonyms, but mempool is like a crappy term in my opinion, because like it's not even always stored in memory anymore. That term is just like left over from early versions of Bitcoin where the entire transaction pool was stored in memory. But so I encourage you to use the phrase transaction pool, but I want you to know the term mempool just so you know what people are talking about. Yeah, so this is where transactions go before they're in blocks. Yeah, and a node that, especially an authoring node that has a transaction pool, it's constantly like revalidating and reprioritizing the transactions in the pool, because the moment that like my authoring node notices like, ooh, hey, it's my turn to author, you want to know which transactions you're going to jam into that block, which ones are like going to get you the highest fees or whatever other heuristic you're using to choose. And so the transaction pool is basically like where the block space market operates. So I mentioned previously there's this like scarce resource called block space, which is produced by blockchains. And all of these transactions are competing to buy or occupy the block space. Now, if there's more block space supply than there is demand from transactions, like great, whatever, they all get in, no big deal. But once the network becomes congested, then there's actual market mechanics that happen here. And this is why you see things like the gas fees spiking on Ethereum or the byte fees spiking on Bitcoin. That's when the demand for block space exceeds the supply and people start trying to outbid each other. So we do have a whole lesson about fees and ordering coming up, but that's like the basics that I'll say right now. Okay, any other questions or comments? Got one.
Okay, so my question is about nodes that maintain the states or the state tree. I'm assuming because there is a transaction pool, there would also be some sort of a state pool, because you're not quite sure which of those transitions are the ones that you're going to commit to and like keep forever. So Would that be a correct assumption that, that they keep that?
Not really. So in order to calculate a state, you have to actually execute the transaction, and some transactions can be like quite expensive to execute. So if you think about like making some kind of swap through some kind of DEX pool, like there's actually a lot of computation that happens there. So nodes don't have the resources to be like keeping track of the post state that would be associated with every single transaction in their pool. So basically, they just do quick checks on the transactions when they come in. So some transactions can be immediately ruled out and thrown away, and others that pass these quick checks are kept in the pool, and then when you go to like make a block, at that point you know the post state. I think Sean wants to answer that too.
Once we get to the database sections, you'll learn that there's also a clever way that Merkle trees can be used such that you can contain the state of multiple different blocks or even different forks while not repeating a ton of data. So in the context where you kind of have this mindset of like a state pool, it kind of is like that, but with using clever Merkle tree stuff. If, for example, your node is keeping track of 2 forks, which is possible.
Yeah, that's a cool slide. I'm excited for everyone to see that. That one rocked my world when I saw it in the last Academy. I'll say even that is for transactions that are in blocks though, right? Not in the mempool, yeah.
And would that be the same technique that's being used to, let's say, validate 2 transactions that are going in the same block that are potentially double spending? Because you have to be validating each transaction's transition to the state against the other transactions that are in the same block.
Yeah. So when I'm building my block, like there's some here. Let's see. Whoops. So like let's say I have this block already. I'm in the process of building this block. So I start with state 4. And like every time I apply a new transaction, I get some like intermediate state. I'm not showing it on my like timeline up here because these are the ones that are like associated with the end of each block. But for sure when you're authoring or even when you're re-executing somebody else's block, you're keeping track of all of those intermediate states. And so like let's say I've put these first 2 transactions into my block that I'm building. I go to grab this one. I start executing it on top of the like intermediate state that came after the first 2. And if I see that it's invalid, like maybe it tries to spend more money than is available, or like it could be invalid for any number of reasons. Like maybe someone's trying to cast a vote, but they're not a registered voter. Then we just throw that one away. We go back to this intermediate state and we grab the next one out of the pool and keep going. Yep. So 5 minutes till lunch. I'm not going to start another coding activity right now. So if we have 5 more minutes of questions, that's great. And if not...